Now let us discuss some of the applications of the Gauss law. And the first application is to find the electric field due to a uniformly charged, let me write it down. Okay, so the first application here is electric field intensity. Electric field intensity due to a uniformly charged straight wire. Okay, so imagine you have a wire. Let me take let's say a white color. All right, let's say you have a wire like this. Let's say this is the wire. Okay, let me draw it a little bit in the middle. Okay, let's say this is an infinitely long, straight, charged wire, and this wire has got positive charges on its surface all along the length of the wire. Okay, and you can see here that I have drawn the distance between the charges to be approximately equal. This shows that this is a uniformly charged wire, means that it has uniform linear density. Okay, uniform linear charge density. Got it? So first of all, if you have a wire like this and if you have the charges all along the length of the wire, then what will happen? What will happen, do you think? What do you think will happen here? These charges will produce electric field in all directions, yes or no? So it will produce electric field in this direction. Okay, let me draw the electric field with blue color. So it will produce electric field in this direction. Yes, all along the line or all along the length of the wire, perpendicular to the length of the wire. Yes or no? So the electric field lines are straight actually. Okay, but just because I'm drawing freehand, I cannot draw it so straight. But you got the idea, isn't it? The electric fields are all along the length of the wire, and if you look from this end, let's say you set your eye from here, this is what you're seeing. This is the wire, and the electric field is going in all directions. Okay, in all directions like this. Right, so this point here is the wire, and these arrows represents the electric field lines. So the electric field line, it goes how? It goes perpendicular to the wire. That is the property of electric field lines. Yes or no? Always they go perpendicular to the surface of the charge distribution, or maybe perpendicular to the length of the wire. Got it? Now, what do we do? In order to find the electric field, in order to apply the Gauss law, you have to draw the Gaussian surface. Okay. Now, what type of a surface are we going to draw out here? We will draw the cylindrical Gaussian surface. Okay, so let me just complete this diagram. Let's say I have a cylinder like this. Let me draw this line from here. And another. Okay, then I complete this part. Right, so let me take this to be the surface which is inside. Okay, so that's our cylindrical Gaussian surface. Okay, so let's say the length of this Gaussian surface is L. From here till here, that will be L. All right, So let's say we want to find the electric field at this point, uh, at this point, okay, at this point P. This point P is actually at a distance r from the wire. And what is r actually? R is nothing but the radius of this cylinder. Okay, so let this point be at a distance r. Understand? All right, now in order to apply the Gauss law, we have to look at this Gaussian surface. Now, is this a closed Gaussian surface? It is a closed Gaussian surface, yes or no? It basically consists of three parts or three regions. Okay, this is the first region out here. Let's call this as region 1. And this is the second region, region 2. And this is the third region, region 3. Got it? So let us choose a small area in this region 1. Let's take a small area here. Okay. This small area, since this face of the cylinder is facing the side, so this surface small area will be in that direction, the area element. It will be in this direction. So let's call this ds bar. Got it? Now what will be the electric field passing through this small area ds bar? Remember, the electric field is always perpendicular to the wire. So the electric field will be coming like this and it will pass perpendicularly. So let me use a different color for the electric field. Electric field through this point will be in this direction. Okay, so this is electric field E bar. Understand? Now let us choose another area in this second region 2. So we choose this area here. All right. Now what is the direction of this area? The area element. Since this area is facing upward, its direction will be upward. Okay, it will be in this direction. So this will be ds in region 2. And what is the electric field passing through this small area? Again, the electric field must be perpendicular to the wire, to the source. So it is coming like this perpendicularly, and through this it is going in the same direction as ds. So this electric field will be in this same direction like this. So this is electric field E bar. Similarly, let us take a small area here. And this area is facing towards the right side. Yes or no? It's facing this side. This is the area ds. Okay? And what will be the electric field passing through this small area? I think by now you know it will be in this direction. Why? Because the electric field is perpendicular to the wire. Got it? So this is electric field E. Okay, it is important to note the angles between the electric field and the area element. In region 1, what is this angle? This angle here is 90 degree. This is 90 degree. This angle here is 0 degree. This angle here is again 90 degree. Understand? So now let us apply the Gauss law. Take another page. Okay. By Gauss law, you have integration of E dot ds. This is equal to Q by epsilon naught. Right? Now what we can do with this integration, if you look at this integration, this is actually a closed integral. Right? Closed integral. But that means it is the integration over a closed surface. Got it? Now, this closed surface, cylindrical closed surface, is actually consisting of three surfaces. Surface 1, which is this surface. Surface 2, which is the curved surface. And surface 3, which is the flat surface. Once again. So what we can do with this integration is we can break this into three parts. integration over region 1 E dot ds plus integration over region 2 E dot ds plus integration over region 3 E dot ds. This will be equal to q by epsilon naught. Do you see? So this is what we can do, and this is the beauty of integration, right? So from one integration you break it into 3 parts. Okay, so from now on you have to just apply you can apply the dot product out here, and we know very well dot product a dot b is what? This will be AB cos theta. Yes, and what is theta? Theta is nothing but the angle between A and B. So here this will be in region 1 you have E ds cos of the angle between E and ds in region 1. Let us have a look at this diagram once again. In region 1, what is the angle? 90 degree. 90 degree. So this will be cos 90 degree. Plus in region 2, E ds cos, what is the angle between E and ds in region 2? Have a look. In region 2, angle between E and ds is 0 degree. So this will be cos of 0 degree plus in region 3, E ds cos 90 degree once again. So this will be equal to q by epsilon naught, right? So this part will be 0, this part will be 0. Why? Because cos of 90 degree is 0. Okay, so you have integration of only in region 2, E ds. Why? Since cos of 0 degree, since this part cos of 0 degree, this is equal to 1. So if you put this equal to 1, you are left with E ds. Okay, and this is equal to how much? Q by epsilon naught. Okay, so again integration in region 2. E, what you can do is you can take it out. Integration of ds only, which is equal to q by epsilon naught. Got it? Now you can take this E. Why? Because the integration is done with respect to the area, and then E here is independent of the area, so it behaves as a constant with respect to the area. So we can do what to the constant? We can take it out. Okay, so you can take it out of the integration sign, and mind you, this is not a closed integral anymore. You see, here it is a closed integral, but you have broken the closed integral into 3 parts. Okay, so therefore I'm not drawing the circle anymore. Got it? All right, now let us look at what will be the value of this integration out here. What is the value of this? Now have a look at this diagram in region 2, remember. Okay, look at this diagram here. We are taking this small area in this region 2 and we integrate this area. Now integration basically means the sum. The sum of what? The sum of these small areas, isn't it? So if I take this area, if I take another area here, so sorry about that. If I take another area here, if we take another small area here, if we take another small area here like this, small area here, small area here, I'm adding all these areas. What am I getting actually? I am getting the area of this curved surface. Yes or no? That is the area. That means the area of only the curved surface. And what is the value of this area? It's actually the circumference multiplied with the length, and that is nothing but circumference is 2 pi r multiplied with the length L. Is that clear? So that is the meaning of summation. All right, summation means you are integration. Integration means you are adding the small areas over the entire area. Okay, so when you add these small areas, what are you getting? You're getting the entire surface area of the cylinder. And what is the formula for the surface area of the cylinder? You take this circumference 2 pi r, multiply it with the entire length. Okay, it means that you are taking this and you're painting this. You're painting this small strips over the length L. So you're taking the small strip 2 pi r, painting it over the length L. So 2 pi r L, you're getting the surface area. Okay. Right. So this value of, let me write it here itself. Let me write it here. So you have E 2 pi r L is equal to Q by epsilon naught. Okay, so E will be Q by 2 pi epsilon naught RL, right? But let me write it somewhere here. I have this space here. But lambda is called the linear charge density. This is actually charged by length. Okay, what is lambda here? Let me write it down. Well, lambda, this is the linear charge density. Okay, so therefore Q by L, that is lambda, so you have E is equal to lambda by 2 pi epsilon naught r. This is the required expression. Okay, so you can clearly see here that the electric field is inversely proportional to the distance. So the farther the distance from the wire, the smaller will be the strength of the electric field. Okay, so this is the first application of Gauss law.